Hey, what's going on YouTube? I am back. We are here with another day practicing mathematics live. Dude, I'm trying to automate so much of this, so that's why I'm a little bit late. I was trying to set up a couple of extra steps in the buttons. But I suppose anybody who's watching this part is not, is almost certainly not live or didn't care that I was late. So I don't even know why I'm saying that. But hello, welcome to my channel. If it's your first time here, my name is John. I am a former mathematics major. I graduated in 2012 with a degree in pure mathematics. Then I worked in Silicon Valley as an iOS software engineer for 10 years. I worked at Apple, Lyft, and Google. And then now I am, how do I say it? I'm trying to become an independent creator, and I'm trying to work for myself. That turns out to be a pretty hard path, even though things do look pretty good. Like, things look like they're growing here on the channel, but it just seems to be a pretty long path until finding something sustainable. And I'm very skeptical that somebody can reasonably try to turn something as boring as a mathematics practice stream into a profitable thing. So instead, that's not my primary goal. Instead, my primary goal, like that is a secondary or third goal. My primary goal is just to get really good at math and really good at teaching math. So I'm a practice streamer. We will be practicing math and practicing linear algebra, practicing teaching and practicing other related skills related to math and related to math teaching live. And dude, like, there's so many video game streamers out there. Like, why aren't there mathematics streamers? There's like one other awesome guy that I know, but unfortunately he recently got freaking hacked by scammers, like crypto bro scammer people. So I really hope K-Theory can make it back and get his streaming privileges back again. Anyway, so in a moment I'll be pulling the iPad up and we can work together on chapter 4 on determinants from this fantastic book by Fraleigh and Beauregard. A lot of people ask why I don't use Axler and why I don't use Strang. Strang is a little too engineering and Axler is a little too pure math. I really think this book by Fraleigh is perfect. It's right in between. It can appeal, I believe, and this is a question to you all, like, for those who are watching and following along with the series, like, if you're an engineer, do you find these problems motivating? If you're a pure math person, do you find these problems interesting or motivating? In any case, this is meant to be a first course in linear algebra, whereas Axler is explicitly stated to be a second course. And I think that that's true. So I have 3 different streams. One is high school math, and we're starting at the very end of high school with calculus. Secondly, we have college math, and I'm mostly focused on linear algebra. And then thirdly, we have graduate level math, which I'm learning for the first time for fun because it's beautiful. And that is mostly focused so far on representation theory, which is applied linear algebra to useless but beautiful problems about symmetry and studying symmetry using the tools of linear algebra. Okay. And then the last thought that I wanted to give there is that, how do I say it? I'm scribbling on the iPad at the same time. Soon we will be graduating up to Axler from Fraleigh. Like, at some point, Axler is going to become the primary linear algebra book. I'm going to feel like, okay, I've done a first course in linear. Let's move on to a second course. I think even then I'll still be revisiting Fraleigh, but as the secondary book. not as the primary book. Determinants are cool, I guess. I think that they are cool, man. I mean, they really are. They're fun. Like, if you like Sudokus, I think you might like Determinants. Okay, so the joke from Lockheed, which I think that we have chat up on screen in the iPad. Welcome to my practice stream. As I said, Fraleigh and Beauregard, this is chapter 4 of Fraleigh, and right in the middle of the book, whereas last time I showed how this was chapter 9, the very end of Axler. That's probably the only stream, at least for a long time, that we're going to be doing determinants from Axler. Because to Axler, we can teach linear algebra without determinants. We can study the most important properties regarding linear maps, and we can study eigenvalues and eigenvectors and even applications of eigenvalue eigenvectors without using the language of determinants, which is a really beautiful idea, and I haven't yet seen that yet, because the standard approach teaches eigenvalues and eigenvectors, which are one of the core, most important ideas in linear algebra. The standard way is to teach it from the determinant. Like my other advanced linear algebra book back there is Shilov, and that one on page 1 just launches you right into gnarly, difficult determinant problems. But that is an advanced second course in linear, or just like a really badass first course in linear, I guess. Anyway, so, okay, I don't have a page for the table of contents, so let's make that. I'm still kind of waking up, so I, apologize. So we've got Fraleigh, chapter 4 is on determinants. What's up, Lockheed, by the way? How are you, bro? How are you? This book is green, and it has how many sections? Oh no, cross products? Fun fact, determinants form a natural transformation between two very simple functors. Ooh, yeah? Oh, I feel like I've heard that before, actually. Okay, so we have chapter 4 on determinants, areas, volumes, and cross products is the first section. Oh, what's my style I like here? I like white pen. Also, if anybody's watching this stream after the fact, the idea is honestly that this is kind of a study with me background kind of co-working stream. I'm joined by my cat, Luna. She's hilarious, and, she'll be making appearances. So, if you want to learn linear algebra, just freaking open a book, man. Like, you might learn stuff from this stream. You could work problems with me, but it's not going to be as effective as just opening a book and staring quietly with a cup of coffee and actually doing problems on your own. On the other hand, what a live stream can provide is community. So if you do want to find people that you can talk about math with and kind of find sort of like mentors and mentees, even like people that you can learn math from and teach math to, that's one of the benefits of a live stream. So I don't know, like I think it's a cool idea that we don't have enough live streamers in math, but if you really want to learn this stuff, please do also just open a book and try to work problems on your own and read the sections, because I'm sometimes lecturing. Lockheed said, oh no, cross products, and it's because this first section includes cross products, which Lockheed is not a fan of. There's an alternative to cross products, just the same way that there's an alternative for eigenvalues. That's funny. So, like, I've learned so much math just by some of the folks who like to hang out here, which I think is amazing. Like, it's difficult to find community and to find study groups and things like that as a math student. At least for me, I didn't do enough of that when I was an undergrad, and I wish I did, because it really helps a lot. Like, to just talk about math with other people. It's kind of like a low-key kind of form of teaching. And they always say, everybody always says that the best way to learn something is to teach it, right? Cool. So, computation of determinants and Cramer's rule. Ugh. I feel the way about that you do about cross products, luck. I feel that way about Cramer's rule. I think that Cramer's rule is a little unnecessary. Yeah. Computation of determinants. And Cramer's rule, named after the character in Seinfeld. Here, we're going to erase that, give this a little apostrophe S abbreviation, move this thing over, and fit it on one line. Dude, check that out. Try to do that on a chalkboard, bro. I really think that the iPad can be an awesome tool in the high school classroom, even. Obviously, I could then share my notes with students after the fact. So, I don't know, yeah. Crazy idea. 4.4, I mean, like, I saw teachers using the iPad really effectively during pandemic lockdowns when we had to be online. I just think that a teacher could be using the iPad with a TV in the classroom. And I don't know if high school teachers are adopting that yet, but like, I'm really interested in the intersection of technology and education, and when it's right to use technology and when it's wrong to use technology. Like I said before, if you want to really learn linear algebra, paper, paper and pen, and just sit down and, work problems, read the book, get a paper book. But, I don't know. For lecturing, I really think that the iPad with an app like Notability can be great. Linear transformations and debts. And this is an optional section. Okay, so these are all of the sections. Hey, random guy watching the stream after the fact, you should go check out category theory. Heck yeah. I suppose it's a good thing I forgot Cramer's rule. I had to learn that for JE, but I never did because I was lazy. Honestly, I think my teacher skipped Cramer's rule completely. I don't feel like I ever learned Cramer's rule in my undergrad first semester course on linear algebra. Like, I don't think I ever learned it. I've learned it recently because I was doing this stream. Well, a year ago I was doing the stream. My first time that I tried it. But yeah, I don't know. I definitely don't think that I ever did Cramer's rule. Okay, let's see. I just want to show you all where we are. Even though this is a secondary, what's it called? The secondary, oh geez, this is chapter 1. This is the secondary source of truth, which is the wrong word to use. This is a secondary source or something. My single source of truth, my one source of truth, is the book itself. Every time I finish a problem, I cross it out in my book. That's one of the advantages of paper. I just know that there's exactly one place where I'm writing everything down, and that I'm tracking everything. So, but every now and then I want to just show you all where we are in the exercise set. 4.2. Here we go. We've done the first 10 problems so far. In exercises 1 to 4, find the indicated determinant, show that a vector is perpendicular to both, find specific computations of determinants, and then show by direct computation these two properties of the determinant. So this is a determinant where the first two rows are identical, and then a determinant where the first and third rows are identical. So next, we're going to work this exercise. But notice now these exercises don't have numbers, dude. Where did the numbers go? Now everything is letters, and some people say that that's when they got, when they started disliking math, when everything starts turning to numbers or letters instead of numbers. For me, that's when I started loving math, actually, because this is a more conceptual problem. And I feel that high school teachers don't know conceptual math on average. They're not able to teach like this kind of conceptual, more proof-oriented math because a lot of high school teachers just didn't do more than one course in it. Like at my university, I think that math ed majors were required to take 2 proof-based courses. Like maybe more as electives, I don't know, but like the required courses, I think that there were only 2, and pure math really changes once you learn proofs. So in a sense, this is a proof. This might be an Axler. All right, areas, volumes, and cross products. Cool. All right, so this is the next problem. I feel like show by direct computation questions are unsatisfying. Like, yes, I can expand and do algebra and it works out, but what geometric fact does that tell me? Yes. I mean, I think that's why Fraleigh says by direct computation. He kind of hints to the idea that there may be more theory, there may be more depth here. There might be something. Yes. Like, I feel like you want to guide a student to the way that you and I think of those follow-up questions. I mean, in my opinion, I like this book. Like, dude, curious, what are your thoughts? On a scale of 1 to 10, having seen a bunch of these exercises from Fraleigh and seeing the way that it is organized, what are your thoughts? Like, I'm very curious, because I think that this is a good first course in linear. What's up, Ta? How's it going? Like, imagine this book for, I guess, the JEE, because you all have linear algebra on the JEE, whereas we don't. We don't teach linear in high school. I said solutions. This is one solution. All right. It is still a direct computation, but hey, I mean, it's a proof. This is a proof. It's a proof by computation, or a proof by, direct computation. Okay, so recall the parallelogram identity for a 2x2 determinant. I'm going to call it the parallelogram identity determinant because determinants begin in the plane And if you have two vectors, you can form the parallelogram by adding those vectors together, and then you get this other diagonal. But then the parallelogram, the area of that parallelogram equals the absolute value of the determinant. The area of the parallelogram, I suppose I could say that area is always positive. Is equal to the determinant of V and W. And then in a 2x2, I can specifically say that this is V1, V2, W1, W2, and using geometry, like using a geometric argument, we can kind of split up this parallelogram and freaking move this right triangle over here, and we can get, doing a little bit of trigonometry and, calculating right angles, and you probably also utilizing the dot product we have this old excellent identity that the angle between two vectors, theta, satisfies this identity. The dot product of V and W is the magnitudes multiplied times the cosine of the angle between them. I hope I can convince you that V dot W, which is in this case V1 W1 plus V2 W2, that's part of where this special identity comes from. V1 W2 minus V2 W1. This is the identity of a 2x2 determinant. And we can get to it by an argument regarding this parallelogram. So the determinant, what I'm trying to get at is that the determinant of A1, A2, B1, B2 is equal to something, and the determinant of B1, B2, okay, yeah, flipping the rows, B1, B2, A1, A2, I don't need an absolute value anymore. The determinant is A1, B2 minus A2, B1. We get this and remember it by this forward diagonal minus the reverse diagonal. For this other one, we have B1, A2 minus B2, A1. Which I can rewrite as negative A1, B2 minus A1, or no, A2, B1. So, and then this is the negative of the first, A1, A2, B1, B2. Therefore, I kind of did it backwards. If I wrote this into, if I typed this up, I would probably start with the first determinant instead of the second, but tomato, tomato, same thing. Therefore, A1, A2, B1, B2. Although I kind of, conceptually, I would prefer to think the way that I did. That this is a modification of the original matrix A. Like, if that's matrix A, then this is like a modified version of matrix A where we swapped the first and second rows. But it all works. It's the same thing. I suppose, like, if we're trying to calculate the left-hand side determinant, then we can rewrite it by interchanging rows, and as long as we flip the sign. Like, this is the important thing. We want to see that we can interchange two rows as long as we flip the sign of the determinant. Yeah. Oops. Cool. And we are done. Boom. Done with that problem. Hey, what's up? Surrender Patel, how are you? How's it going? Yeah, JE is multiple choice based, so it's mostly computational rather than conceptual. Right. So I think that this book has computational linear algebra, which is often your first intro to linear algebra, and that's how you all teach it. It seems like, then, like, in your country. What's up, Ta? How's it going, bro? I'm sorry I missed your message. How's it going? Long 9 training days. Tell me more, dude. That sounds hardcore. Like, I would never be able to do something like boot camp, bro. Like, no. That's not me. Okay, so let's cross them out in pen, in my book. We did it. Now, let's do one more, because this is going to be very quick, just to do another. It's the same idea. And then this way, we're moving on to harder problems each time. So again, section 4.1. This time it's problem 12. Show by direct computation that a 3x3 determinant C1, C2, C3 that the same property holds if we interchange the first and third rows. Oh wait, no, the second and third rows. So this is getting us some practice with the 3x3 special identity. So I'm going to, oops. I am going to append an extra copy of the first column and the second column. Oops, what am I doing? A1, A2, B1, B2, C1, C2. Then I multiply, similar to the 2 by 2 determinant, I multiply the negative diagonals, or I call it the forward diagonals because I'm thinking of determinants. Like, these are the positive diagonals, even though the slope is negative, which is a little confusing. But A1, B2, C3 plus A2, B3, C1 plus A3, B1, C2. A3, B1, C2. Then we need to subtract each of these reverse diagonals. I'm going to alphabetize these because multiplication is commutative, so this is going to help everything be organized. Oops. In the rest of my proof. A1, B3, C2. Minus A2, B1, C3. Okay. For the sake of presentation, maybe I only keep these two, just so that, and I keep the color. So, or, even better, I should just do thinner lines through and keep them up. So again, I'm thinking about how to present this to you all and get some practice just drawing it, writing it out. Like if I do kind of lighter dotted lines through those diagonals, then you can see them. I worry a little bit that there's definitely bias to, people who, there's definitely bias in my teaching in this presentation style to people who aren't colorblind. Like, I worry how much, how much of this would be impacted if somebody were colorblind, because of course I want everything to be inclusive. I would have to be very inclusive to everybody in my lectures. So I don't want to lean too much into color, but yeah. I mean, I learned all this on a chalkboard, like with one color chalk, like for the most part. What's up, Zafarb? How's it going? What's up, dude? I literally have no reference point for what constitutes a course in linear algebra, since my linear algebra knowledge is just collecting bits from other branches of math. Right, yeah. So I keep forgetting. You studied engineering in college, and then now you're self-studying math as a hobby, right? You never took any, like a proof-based course in linear algebra, right? And yeah, JE is like matrix theory. But for a lot of engineers, you just need to know matrix theory. So we want to be teaching matrix theory and matrix computations with concepts as well. This can be proved by the volume, yes, areas of the area of the parallelogram and the volume of the cross product, which is like a three-dimensional, it's like a three-dimensional parallelogram. It's called a parallelepiped or something, but nobody has ever heard of that before. So, if I start from the right-hand side, I think that this is going to be the best way to prove this identity. I'm going to start from the right-hand side and then show that it equals the determinant of the original matrix A. So I want to label also the determinant of A is this, and then the determinant of this modified version of the matrix is this. And then this is negative bracket A1, B3, C2, plus A2, B1, C3, A2, B1, C3, plus A3, B2, C1. Minus A3, B1, C2 minus A1, B2, C3, A1, B2, C3, and minus A1 or A2, B3, C1. Kind of ran out of space. A2, B3, C1. Okay, now I did this one in my head without appending or not in my head, but like I did it in place without actually appending those two extra columns. As you continue practicing these, you can start doing them this way. So, yeah. Let's just emphasize that example, A2, B1, C3. Something that you might notice that's interesting, I think that this is a cool thing to notice. Here we have 1, 2, and 3. Here we have 1, 2, and 3. Here we have 1, 2, and 3. Here we have 1, 2, 3. 1, 2, 3. And 1, 2, 3. That's not a coincidence. And every term is from row 1, row 2, row 3, row 1, row 2, row 3, row 1, row 2, row 3. All of them are, it's all the permutations of those indices and columns. This creates something called the permutation group. Like the this creates something called the permutation group. Like 1, 2, 3. These are elements of, like the first one is ordered as 1, 2, 3. The second one is ordered as 2, 3, 1. The third is 3, 1, 2. 3, 2, 1, 1, 3, 2, and 2, 1, 3. So this is something to notice. That's theoretically, conceptually a cool property about the determinant. Let's keep moving, though, to work this exercise. So if I distribute the negative, then I see that we have, and if I reorder them in our convenient way, where I want A1, the A1 term first, which I'm getting here, plus my A2 term, which is there, B3, C1, plus my A3 term, which is A3, B1, C2. And distributing the negative, I suppose, all of my formulas, I haven't factored out the negative, so I'll keep the negative distributed in this case as well. So A1, B3, C2 minus A2, B1, C3 minus A3, B2, C1. Right? Now we can compare one by one to the determinant of A to our special formula for 3x3s. A1, B2, C3. I'm just going to read out the index names for the reason that I said before. I've sorted all of them in the multiplication, so it's always A, B, C, like row 1, row 2, row 3. So I can just check 1, 2, 3, 2, 3, 1, 3, 1, 2, minus 1, 3, 2. Wait, what? 1. Oh, I didn't sort the order of the red ones, but there's 1, 3, 2, 2, 1, 3, and 3, 2, 1. So I checked, I saw every term is in the other one, and then therefore this is the determinant of the original matrix, and we are done. Let's see. What's up, Surrender Patel? How's it going, dude? 3x3 determinants brings back PTSD. Huh, that's not how we learned to compute it. Interesting. I suppose this method feels easier. Are you talking about computing like with the duplicating columns 1 and 2? I think it's awesome. I think this is the best way possible to remember this crazy freaking formula. How did you learn it? Also, yet my actual linear algebra knowledge is 0. First proof-based math I did was group theory. Oh, no shit. Okay, maybe that explains to me a little bit why you're interested in watching my stream on linear algebra so much. That's cool. Dang, I didn't know that. I mean, you know enough. Like, I think that Are you actually learning some linear algebra from this stream? That's pretty cool to me. But yeah, I think that this duplicating the first and second columns trick is super freaking useful. And then once you get used to that, then you can start doing it in place. Is this how you learned how to do it? Like this method? Or were you just told to freaking memorize this horrible equation? I mean, you could memorize this equation in terms of the symmetric group and like the orderings of indices. But that gets really, I don't know, that gets really complicated and really confusing really fast. And you have to define when you use negative signs instead of positive. And it depends on how many permutations, counting an even or odd number of permutations of 1, 2, 3. So, like in this case, 1, 2, 3 maps to, say if we swapped 3, 2, 1, we get, oh, no. If we just swap 3 and 1, then we get 3, 2, 1. So the swapping element is the permutation 1, 3. So there's only one permutation needed here. So so the sign is -1 to the 1, because that's the number of these permutations. But that's like a really weird, complex way to try to learn a 3x3 determinant for the first time. But I just wanted to share with anybody watching the video that there are multiple ways to conceptualize and think of these determinant properties. Again, Axler prefers to think of it in a much more conceptual, framework, which is also really cool. But I don't know. I mean, as I understand it, engineers have used this much more. Like determinants from matrices to calculate, to keep our bridges from falling down and stuff like that. Okay, let's keep going. That's 2 exercises. Cool, you're eating and you'll explain in a bit. Nice. Awesome. Let's go on to 4.2, which I believe is now going to extend this definition to n dimensions instead of 3 dimensions. Yeah, the determinant of a square matrix. The determinant of a square matrix A, which is a grid of Aij entries, is going to be, we can define it as a alternating sum I want to say j equals 1 to n, because Aij, even though this is an overloading of the letter j, which means that here j is just bound to this sum, right? Whereas here j is referring to the indices of the elements. I think it's just nice if they match, if I'm using the same letter for the two. But I could use anything I want. I could use an emoji or something here if I wanted to, or a Greek letter just to scare people. But this will be an expansion along the first row and the jth column. So I take all the coefficients and then I multiply by the determinant of Aj, where Aj is obtained by removing row 1 and column J from A. So this is like a modification of the original matrix by crossing out always the first row and then the jth column. This will define the determinant for any n by n matrix. And I just wanted to show that these are just two different notations. So I use the bar notation and det A interchangeably. So here I'm using the bar notation. So I wanted to make sure I at least write the bar notation here. Okay. So we could see that the 3x3 and 2x2 cases satisfy this. So I want to check that it matches A1, and now, as I said, I'm going to cross out the first row and first column. And in fact, I'm always crossing out the first row. Also, let's, -1 to the 1 plus 1 is a positive sign. I'll only do that for the first one, just to show it. But because j is going from 1 to n, these signs are going to start from +1 and then -1. So positive, negative. Right? And if we cross out the first row, first column, then the cofactor matrix is B2, B3, C2, C3. And as I said, these signs are going to alternate. Then the second cofactor, we're going to remove this, the second column, and multiply by by that coefficient minus A2. The minor matrix is B1, B3, C1, C3, plus A3 times this minor matrix. So plus A3 times this minor matrix, B1, B2, C1, C2. And then this is A1. Now we can just use our handy dandy 2x2 fact, like multiply the negative diagonal minus the positive diagonal. A1, B2, C3. I'm already going to distribute A1. So minus A1, B3, C2. Now minus A2, B1, C3. Minus negative is A2, B3, C1 plus A3 B1 C2 minus A3 B2 C1. Now, if I reorder, let's try to get clever about this. If I literally reorder look at how fancy that was. If I literally reorder those and then check the previous equation, we would see that this is the determinant of A from the previous volume of a cross product. Well, wait. The volume of the parallelepiped. The volume of the parallelepiped formula, this is the same definition for a 3x3. So we see that correctly, this generalization, this is what in math we would call a generalization. It matches the 2x2 and 3x3 special, real world determinants. Like our real world is in 2 and 3 dimensional space. It's not in 4-dimensional space. Fight me on that. Fight me on that in the comments section. But yeah, we see that this method, it still works. Matches our previous definition that we defined. So, knowing that, now we can take a look at a problem. The determinant was an inductive. Yep. Okay. So yeah. You learned the n by n determinant, but you didn't learn the special formulas for 2x2 and 3x3, or you memorized the 2x2 definition, but you didn't see the 3x3 special definition. The 3x3 one is super handy because 3x3s, I don't know, at least in homework sets, they pop up a lot. And yeah, you can definitely, so I was thinking as I was writing this, I was like, oh, I bet that this is exactly what you did. But this is a bunch of fucking steps, dude. Like, you can go straight to this one by looking at the 3x3. I can write out, as I did in the previous one, I can write out this, jump right here. It's very useful, like, to learn this 3x3 version. So I've done a lot of conceptual determinants so far with, A1, A2, A3, B1, B2, B3. When I try to go one step above conceptual to a concrete example, I love to see if I can use the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, just so I can work with actual numbers, but in some sense, this is still close to conceptual, because if there's some random pattern in this, then it would be surprising. Turns out that there is in this case, but we'll see it. 1 times 5 times 9 plus 2 times 6 times 7 plus 3, 4, 8. minus 357. I'm just saying those, but I mean 3 times 5 times 7, but yeah. 168 minus 249. Right? Like, it's not like I memorized that. Like, I went straight to that step and I didn't compute it as 3 2x2s. Let's see. Let's see if we can be clever about this and factor some convenient things. Well, 1 times anything is itself. I can factor out a 3 from the first 3 terms. I'm focusing on the positive ones right now. And then I have 3 times 5, which is 3 times 5 is 15, plus 2 times 3 times 7, or wait, no, 2 times 2 times 7 is 4 times 7 is 28. I factored out a 3, and then 4 times 8 is 32. Well, 28 was 4 times 7, and 32 is 4 times 8. So this is the same as 4 times 7 plus 8, which is 15. And then in the second line, what can we look for? Again, we can factor out a 3. 5 times 7, maybe I'll leave them like this to try to spot common factors. 2 times 8, well, 2 times 8 is, let's just leave it. 2 times 8 minus, oh wait, oops, I factored out a negative, so these are all positive signs. 5 times 7, 2 times 8, and I factored out a 3, so we have 2 times 4 times 3. I could factor out a 3 if we're crazy. This is 5 times 15. Minus 5 times 7 minus I can factor out an 8 from these two, and I get 8 times 2 and 8 times 3, so that's the same as 8 times 5. And now we have 3 times, 5 times 15, and then factor out a 5 from both of these, and we have 5 times 15. And voila, this is 3 times 0. It turns out that for this random example that I came up with to try to check a 3x3 calculation of a determinant, and I've remembered this ever since. Like, the first time that I ever worked one of these 3x3 determinant problems on stream, I made up this determinant, and I was like, oh, I bet, like, there's no way that's going to be a special number. But in this case, it's actually kind of cool. This one is 0. The reason that it's cool if the determinant is 0, we'll see at some point that determinant of A is 0 if and only if the rows or columns equivalently are linearly dependent. So there's some combination of rows 1 and 2 that equals row 3, which is pretty cool. Let's see, 2 times the second minus the first. Could that be it? Because 8 minus 1 would be 7. Yep, 10 minus 2 is 8. 12 minus 3 is 9. So 2 times row 2 minus row 1 is row 3. That's kind of cool. That's a cool little trivia fact. Like, I've memorized, I've learned this, I've known this ever since, because I made up my own problem using 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I don't know. Someday I'll use that in the real world. Someday I'll come across that matrix and I'll know it immediately. All I wanted to show was that once you get good at the special formula for a 3x3, I can skip these 2 tedious lines, and that's a lot less writing than just going straight to this one. So I think knowing that also helps a lot if you needed to calculate a 4x4 through the inductive definition as well. But yes, fun fact about this process, you can do it across any column or row, not just the top column. Absolutely. We will be writing down those properties of the determinant in this section, in fact. So in this section, we prove, Fraleigh proves a lot of very useful, I'm just going to show the book for this because I don't want to write them out. I've done this in streams before. I've taken notes on this section. And his definition is just ever so slightly different, like different freaking names or something. Like, he defines the cofactor Aij prime to be that, and then defining the nth order determinant this way. It's equivalent, it's the same damn thing. I prefer my way of writing it because then it's all in one line rather than like referencing, refactoring and extracting out what Aij prime is. Yeah, and the way I wrote it is what I've seen in other books as well. Okay, so find the cofactor, so we get 1. It's worth doing it like once in your life to calculate a 4x4 or a larger determinant using this tedious equation of expansion, like inductively building it from smaller determinants. But as Fraleigh says, computations of determinants, even of moderate size, is a tremendous chore. So we have better tools. Like, you don't want to actually use that definition, but we can use the definition to, and this is a funny sentence, I don't think I've read this. According to modern astronomical theory, our solar system would be dead long before a present-day computer could find the determinant of a 50 by 50 matrix using just the inductive definition 4.1. And this is an exercise. So that's kind of freaking awesome. So, like, you might say, like, is this a moderate matrix? Is this a moderate size? Yes, absolutely. That's tiny because ChatGPT and other AI LLMs are using, not 50 by 50, but like literally 2 billion by 2 billion kinds of matrices. there's a tremendous amount of optimization and algorithms, and they may not be finding determinants of those giant matrices. But I just want to point out that in the real world, one of the most useful things, like linear algebra, is one of the most applied fields of math right now, because, I mean, for a long time, even before AI, like really in the age of the computers, determinants and linear algebra matrices are so prevalent. It's just used everywhere in anything digital. And the matrices for these real world engineering problems, obviously we absolutely need a computer to calculate gigantic matrices like this. And yeah, that's what I'm trying to say. Like if a 50 by 50 would kill the universe before we're done calculating that, like, just imagine the fact that in the real world, we are actually calculating much, much bigger matrices. So, sneak peek in chapter 10, we saw that computation with the naive definition is O of n factorial, whereas we can get a major speed up on this. And I need to remind myself, but I believe that we get it to O of n squared. And in chapter 10, we find some factor like O of n squared over 3 or something. But in computer science, O of n squared is the same as O of n squared over 3. If anybody doesn't know what the hell I'm talking about here, this is sort of like approximately equal to n factorial operations versus n squared operations. Dude, you went through 2 years with the slow method? You went through 2 years of calculating 3 by 3? Dude, we did 1 day doing the dumb ways, and then we went on to the more intelligent ways. That's crazy. And you practice with the stupid way. Dang, dude. I mean, even for 3 by 3s, I start using the properties that are valuable. I don't know. I don't see what this theorem is about. So general expansion by minors. R and S be any selections from the list of numbers 1 through n. Oh, okay. So this is saying that you can... So that you can expand by any row, or you can also expand by any column. And this is a theorem that we can prove from the simpler definition. And math is a deductive science. We start with a simple definition, even if it's impractical. It's not something that you want to do in the real world. But starting from a formal definition, we can prove facts that make our lives easier. So we can calculate this determinant. Yeah, like in this example, we can expand by minors at each step on the row or column containing the most zeros. So from the first, row 5 has the most zeros. So we can quickly rewrite determinant of A as 2. Let's see. Since it's odd and the signs flip positive, negative, positive, negative, positive, we are going to calculate this as a positive 2 times the 2x2 or the 4x4 determinant that we obtain. So we reduce it to that 4x4 determinant. And then in this step, we can expand along the third column because it has a bunch of zeros. And then we go, again, positive, negative, positive, negative. So again, we still have positive 1. Wait, shit, did I? No, my bad. The reason was, we went positive, negative, positive, negative, positive in the coefficients, not which column or row we are expanding on. So I should have written my positive negatives along this row, not the column. I keep getting this one backwards, but yeah. Here we go. The signs are positive 0 for the coefficient, negative 1, positive 0, positive 0, and that's where we get positive 1. And cross out that row and column. We get this 3x3. Now we could use the first column or the second row. I would personally use the first column, I think. And I think that's what they did too. Yeah. If you expand along this column, now we need to break this into 2 smaller determinants. So positive 3, negative 0, positive negative 1. So positive 3 times that 2x2 minus 1 times the this other 2x2, and then we can calculate it and we can get 12. So this is a super, super useful theorem that helps. It's so much more quicker, more efficient than doing it from the original definition. Now, example 4, this is a cool conceptual one. Like if you have a triangular matrix, well, you can expand along the last row, then the next to last row. Every time that we expand along the last row, we chop out that column, so then the last row always has zeros followed by a non-zero number, a potentially non-zero number. So we just need to keep track of the negatives. But as you do that, you end up seeing that it is just the determinant of an upper triangular matrix is the product of all of the diagonal, which is awesome. That's a really useful fact to use as we move forward in computation, especially as we see some later properties. Now, another property that is freaking great is the transpose property. So determinant of A is the determinant of a transpose. This is kind of like justifying the fact that we can expand along the first column instead of the first row. But yeah, that's one property. There's a proof if you want to read that. It would be very good for you. Another property is the row interchange property. So if any 2 rows of a square matrix are interchanged, the determinant is the same with a flipped sign. It flips the sign of the determinant. So determinant of A equals negative determinant of A prime, where A prime interchanges to rows or columns. This property, this theorem, doesn't say that it works for columns as well, but the fact that if you combine that with the previous one, then you get the fact that you can do it with any columns, because we can just rewrite rows as columns and columns as rows. So, and again, there's a proof for this. Equal rows property. Now, if any two rows are equal, then the determinant is 0, which is awesome. And we can prove this really nicely from the interchange property. And look how short this proof is. I should memorize and continue practicing that, but let's keep going. Property 4, scalar multiplication property. So scalar multiplication property says that the determinant of A is k times the determinant of A prime. Here. Determinant of A is as k times the determinant of A prime, where A prime divides any one row or column by k. We can think of it as like, quote unquote, factoring out a constant. Let's just see one example. 2, 4, 6. 1, 2, 3, 4, 5, 6. Oops, not square brackets. Our notation is straight lines for... Here we go. Straight lines for the determinant, right? This is 2 times 1, 2, 3, 1, 2, 3, 4, 5, 6. And now I wasn't even planning this, but rows 1 and 2 are identical, so this is 2 times 0, which is 0, of course. We could also go this way. As I said, we can factor out a common factor from any row or column. And I noticed that the third column also is divisible by 3. Every entry is divisible by 3. 2, 4, 2, 1, 2, 1, 4, 5, 6. Okay? And maybe right now I don't see immediately why that would also equal 0. Well, the first row is twice the second, though. And we can see that that is going to annihilate this determinant. 1, 2, 1, 1, 2, 1, 4, 5, 6. Right? And now, by the row interchange property, rows 1 and 2 are identical, so this is 6 times 0. Cool. Heck yeah. And then there's a proof. It's really worth reading. Let's keep going, though. So now we can use those properties that we've proven, or at least Fraleigh proved, and we can just freaking apply that and use it everywhere. Like here, I see that this row is all divisible by 3, so I bet that's the first, that's going to be the first application. And we can get pretty far just with this. Like, what would that row be? It would then be 2, 1, 3, 4, 6. So I could replace that row with 2, 1, 3, 4, 6. And then 2, 1, 3, 4 is repeated in 3 different rows with different... So then, yeah, I see 2, 1, 3, 4 is popping up here. It would be popping up right there, and it also pops up here. So my hunch is if we expand by that last column, we would get some convenient stuff. Or, wait, property 4, yeah, they factored out 3. 2, 1, 3, 4, 2, 2, 1, 3, 4... Oh, I didn't see it. 2, 1, 3, 4, 2. Oh, shoot. Okay, my bad. When I factor out 3 from that third row, when I factor out 3, then the last entry is a 2. And then, immediately, rows 1 and this row are equal, so then we're going to get a 0 determinant by property 3. Row interchange and scalar multiplication, blah, blah, blah. Then we get a row addition property. I like to write this one slightly different. I combine with the next property, I think. But row of determinant of A is exactly equal to the determinant of A prime, where A prime is built by any row you replace with itself plus a scalar multiple of any other row. So we can add rows to other rows and preserve the determinant value. So, we'll see an example at some point. Theorem, determinant criterion for invertibility. A matrix is invertible if and only if the determinant of A is non-zero. The multiplicative property, determinant of AB is equal to the determinant of A times the determinant of B. Let's get an example. Well, you could multiply the matrices together, or you could calculate the 2 determinants separately. Determinant, if you assume that the determinant of A is 3, then what is the determinant of A to the 5th? Well, determinant of A to the 5th is the determinant of A times A times A times A times A. And if you apply that previous property that we just mentioned 5 times, we get determinant of A to the 5th. So if determinant of A is 3, then we get 3 to the 5th, and 3 to the 5th is whatever. 243. And then determinant of A inverse. How do we get... Well, determinant of A inverse times A is equal to the determinant of the identity matrix, which is 1. Determinant of A inverse times A is determinant of A inverse times the determinant of A, which is 1. And so, therefore, since determinant of A is 3, then determinant of A inverse is 1/3. So, yep, we get determinant of A, and they did pretty much exactly the same steps that I was thinking. All right, and then there's a summary. Now, in the next section, which I don't think I'll carefully read through the whole thing, but now we're going to get to even more efficient algorithms for calculating determinants. And if we think of the previous properties, combining the facts that the simplifications, those tools or something. I really like the word tool in math. Combining tools from section 2, a lot of those steps look very similar to Gaussian row reduction, right? So if we row reduce a matrix to row echelon form, well, A is a square matrix, so I can even write U, because a square matrix in row echelon form is an upper triangular matrix. Then, as long as we use exactly the properties that we've learned before, then we can just do our regular old row reductions that we learned in chapter 2, which is awesome, because then that simplifies our lives even better. The one property that really you need to watch out for, I think, is that the determinant of A equals determinant of A prime when you replace a row by itself plus or minus another row. The thing that is a gotcha that's different versus our row reductions in the past is that you can't multiply the row at the same time, and say like it's 2 times row, replace row 2 by 2 row 3 minus 3 row 1 or something. Because then when you multiply the row by a scalar, you need to track that. You need to track the factoring. Like if you multiply a row by a scalar, then you need to also, if you multiply by a scalar, then you need to divide the new determinant. But anyways, yeah, we can compute determinants using row reduction. Like all these previous properties that we've just talked about are very similar, or like they are operations that we do in row reductions. So let's look at an exercise. Find the cofactor of 5 for the matrix in exercise 2. We're looking for the cofactor of 5. Is the A3, 1 cofactor. So I believe in this book we are putting our positive and negative signs in the cofactor. So this would be a positive 2 by 2 determinant. We cross out the first and third columns, and we get 0, 6, 1, negative 1. And the cofactor, I don't know if we should say that it's that we leave it as that, or I think that we would actually compute it. The cofactor of 3, 1 is negative 6. So I got negative 6 here. Find the cofactor of 3 for the matrix in exercise 4. In exercise 4, cofactor of 3 then would be A21 prime. Remember that the signs flip for every term. So negative 2 by 2 determinant -1, 2, 2, 1. And I got that by crossing out the first row and second column again, which is 1. Yeah, 1 plus 4 is 5. Find the cofactor of 7 from exercise 8. The cofactor of 7 is the cofactor A14 prime. Positive, negative, positive, negative. So this is negative determinant of this 3 by 3 matrix, 6, 1, 0, 8, -2, 1, 4, 1, 0. We can, at this point, start using our properties. I'm going to expand along that column. So positive, negative, positive. We have 2 negatives multiplied together. We have +1 times a 2 by 2 determinant. 6, 1, 4, 1. Which is 6 minus 4, which is 2. Find the cofactor of -5 in exercise 9. -5 is here, and that's the only -5 it looks like. They're not trying to trick us. So we're looking at A3, 1, 2, 3, 4, 5, 6, A36 prime. We can, if we're expanding along 3, 4, 5, 6. If we expand along a row, positive, negative, positive, negative, positive, negative. I guess it depends on whether you're expanding along a row or a column, whether we say that this is a positive or negative sign. Yeah, interesting. Okay. A36 prime, if I expand along the row, then it is going to be negative 1, 2, 3, 4, 5 by 5 determinant. Dang. 1, 2, 0, -1, 2, 6, 2, 8, 1, -1, 4, 5, 4, 5, 1, 1, 2, 0, -1, 2, 1, 0, 1, 8, 1, 1, 0, 1, 8, 1. Okay, y'all. We could start doing all our row operations and using all of those properties and look for factoring things, but the very first property I'm going to look for is 2 identical rows or columns, and we get 2 identical rows there in rows 1 and 4, so this cofactor is 0. Heck yeah. Yeah, I don't know any Hindi. What's up, y'all? Sorry, I haven't been reading the chat as much, but bro, how do you all feel? We just solved 4 exercises from this section, so in the future we're going to start getting to some more conceptual problems. Especially, I love these conceptual true-false problems. I think the true-false problems in this book are just phenomenal. And Taalman's book also does the exact same thing. Yeah, some people just really like to delete messages. It's kind of weird. I don't know why. Okay. Thank you. So next, we're going to look at the exercise set. How far are we? Oof. Computation of determinants and Cramer's rule. Y'all excited for a 5x5? Hi, JC. Let's forget math and go to Hawaii. Yeah, we can go to Hawaii. I guess I could read all the messages that he sent before he deleted them if I went back and rewatched all the video. You want to go to Hawaii? We can go to Hawaii. There we go. There's some Hawaii for you. Yeah, matrices are very useful. We use them all the time, dude, in engineering. 5x5 with more zeros. Yeah, there's a bunch of zeros in this one, so it's not as bad as it might look. But I don't like, even if there are zeros, dude, I do not want to expand this as 2 separate determinants. That is not the right way. And that it sounds like that might have been how you freaking learned it, man. So you're learning something. Instead, I still want to compute this by row reduction. Unless there's, the only property I want to use immediately is any common factors. And I can factor out a 4 from the last column. But that's it. So let me make sure, we may have used this, or we may have already worked this example. The book is the source of truth for which problems I have worked. So I get to cross out 4 from that previous section. Heck yeah. Aha, we did this problem last time. I had a hunch that we may have already worked this problem. Okay, now we're going to do number 10, which seems like it's probably quite similar. Last time that I worked these problems, I noted this interesting property about blocks, that we have these block matrices, and it's like diagonal blocks. We've already been working through Jordan canonical form from later, chapter 9. So in this, I see that this matrix is 2 Jordan blocks, which is, oh wait. No, it's not. It's 2 block matrices. They're not in Jordan form, right? Yeah, they're not in Jordan form, but they are block matrices. Then it turns out the determinant of A is the determinant of block matrix A1 and block matrix A2, which is pretty awesome. I don't know. I suspect that this is also the product of those two block matrices, but I wouldn't be surprised if the sign changed to like a negative determinant or something. Cool. You're learning new ways to compute the determinant. Dude, that's awesome. You taught me a lot of math so far. I can teach you some math too. Heck yeah. Okay. Yeah, like this method is actually what computers implement as, like this is actually the real implementation of determinants. Where are we? That's kind of cool. It makes me think I should make a short or something out of this, because if JE tests and, you know, JE tutors are teaching the expansion, like it's tremendously tedious. It's not the right way. I'm just going to call this section 4.3 on computation of determinants, maybe. So we get a more efficient approach. I always like to say solution, man. I always do it. It makes me happy. I'm going to say, I'm just going to give this bars here and cross out that 10. This is equal to, as I said, I can look for common factors, but I don't see any. Yeah, there's no common factors in any rows or columns. But I can do some row operations. Let's do these kind of carefully. Or, okay, so if I multiply the second row by, let's multiply the first row by 2. So if I multiply the first row by 2, I need to take half of the determinant. So 0, 0, 0, multiplied by 2 is 6, negative 8, right? Like if I factor out a 2 from that first row, then 2 times 1/2 is 1. And then we're back to the left-hand side. And I'm just going to try to take shortcuts and just say the rest is the same as the previous equation or the previous entry. Now, now I can subtract 3 times. Well, I'll write the 2 relevant lines right now, even though the second row is identical. I just want to see them next to each other. Now I can, as I said before, I can replace a row with itself, no scaling, like row 1 plus or minus row 2. I'm going to do minus 3 times row 2. Then we annihilate that 6. So yeah, we got 0, 0, 0, 6 minus 6, and then negative 8 minus 3. And then 0, 0, 0, let's just write it. 2, 1, negative 1, 2, 4, 0, 0, 3, 1, negative 2, 0, 0, and 5, 1, 5, 0, 0. Now I can expand along the first row, and then we have negative 11 times 1/2. And we need to get the right sign. Positive, negative, positive, negative, positive. So the sign is negative 11/2 times the 4x4 determinant. 0, 0, 0, 2, negative 1, 2, 4, 0, 3, 1, negative 2, 0, 5, 1, 5, 0. Cool. Now I can expand again along the first row. But this time the sign is going to alternate. Positive, negative, positive, negative. So we have negative 2 times negative 11/2, which is now positive 11 times this 3x3. Negative 1, 2, 4, 3, 1, negative 2, 5, 1, 5. I could go to my 3x3 formula, but I still prefer row reduction. I'm going to add 3 times row 1 to row 2. So I keep row 1 the same. And I have negative 3 minus 3. 1, and yeah, I'm adding 3 times row 1 to row 2. So 6 plus 1 is 7. 12 minus 2 is 10. While we're at it, add 5 times row 1 to row 3. So 5 minus 5 is 0. 10 plus 1 is 11. And 20 plus 5 is 25. Now, I think it's going to be best to, we're going to have, now we can expand along the first column. So we have negative 11 times a 2x2, which is easy. 7, 10, 11, 25. I could factor out a 5, but whatever, let's just do this. Negative 11 times 7 times 5 squared minus 2 times 5 times 11 is, let's factor out a 5, and we get negative 55 times 7 times 5 is 35. 2 times 11 is 22. Negative 55 times 13. And that's a perfectly fine way to write this, in my opinion. But that would be negative 550 minus 3 times 55 would be 165, right? And then that is going to be negative 715, I think. Did I get that? Yeah, Lockheed, you can be a mod, bro. You should absolutely be a mod. Why have I not? I'm not very good about modding people. And if there's somebody typing a bunch of stuff and then deleting it, and it's showing up in because I'm trying to stay focused, of course. So if there's anything that I wish were not showing up on screen, please feel free to time out the person or block the person, whatever you feel is right. I totally trust you on this. Blue power, dude. Type something. You got blue power now. Yeah, row addition property is the most OP one. Yeah, the row addition property is like the super powerful frickin' Gaussian reduction one. Damn, there's a whole FAQ I need to read now. Oh, did you get like a pop-up or something? Bro, don't worry about it. You can figure it out as you go. You're a smart guy. Don't bother, dude. That FAQ is for people who don't know math, you know? Well, I can tell, dude, Manu loves coffee. I love coffee too. I appreciate your presence, and as far as I can tell, you're not, if I understand correctly, you're not saying anything offensive, but don't delete your messages unless there's a good reason. Like, I don't like this idea of like sending messages and then deleting them. It's very distracting to me. And for all I know, you could be typing anything. So I'm going to put you in a timeout for 30 minutes. Now all your messages would have been deleted anyways, but, okay, so I think that this is the right answer. It's an even problem, so I can't just check the back of the book. And if I made a little typo somewhere, it's no big deal. The next section is kind of mathematically cool. I'm wondering why oh yeah, no, now all his messages are deleted, I guess. But I just did. YouTube on tablets should be fine. Like, if you can see his message, I think you can click on a message and now you have extra powers. I mean, you could do it if his messages weren't deleted, I think. Alright, yeah. Keep it chilly, everybody. Keep it chilly in the chat. Okay, well, this next section, section 4.4, is optional. But it's quite nice and interesting. We have a theorem that we don't prove, but we have the definition of an n box in Rm. So, like, what is an n box in Rm? Well, for example, in the plane in R squared, a 1 box is a line segment. 2 box is a 2 box is a parallelogram. And then in 3 dimensions, we get similar stuff. We get a line. We get, a parallelogram along a plane. And then we also get a parallelepiped, which creates a box. So far, our determinant that we've defined as, for 2 by 2, the determinant of a square matrix, which is a 2 by 2 like so far our determinant properties and facts required that the matrix matches the dimension, that the matrix is square. But if we only have two vectors in R3, that defines a 2 by 3 a 3 by 2 matrix. So I'm saying that now we're going to see a theorem that shows that even in R cubed, we can find the volume of two vectors in R3, which is, I didn't know this. I had never learned this until I started streaming and working these optional sections, which I thought was actually kind of cool. So the n box in Rm is determined by n independent vectors, and it's going to be all combinations where the coefficients range between 0 and 1. So we're not finding like the area of the entire plane, like the span of A1, A2, because this looks like the span, but this is all, like, this doesn't have a requirement on the coefficients, whereas this requires that the coefficients are between 0 and 1. So it's similar to span, but it's not the same. And if the vectors are dependent, then the set described is a degenerate n box. So we get some degenerate math coming up here. There were no messages from him to click on before you timed out too. Of course, absolutely. But later, if it starts coming up again. This reminds me of n-simplex too. If you restrict the coefficients to be not strictly increasing, then you get an n-dimensional pyramid. Ooh, I've never actually learned that. I've heard the term simplexes or simplices. That's awesome. I didn't know that. Heck yeah, dude. Okay. So a 3 box in Rm, even in higher dimensions, we still can think about the 3 box, like a 3-dimensional box in 10-dimensional space or something, which is pretty neat. And then there's a theorem that apparently is complex and needs work to get to, that is out of the scope of this book. I don't know what's up with that blank page, but they say that that the formal definition of the volume of an n box appears in the M via this formula. So A is not a square matrix. I like to say it's a rectangular matrix, but there's going to be a nerd out there who criticizes that. But for any square matrix, or for any rectangular matrix, the volume is the determinant of A transpose times A, followed by the square root of that quantity, which is neat. Yeah, so A is any rectangular matrix, and the vectors are written as column vectors. So then the volume of an n box in Rm, this is back to generalizing the 2 by 2 fact that we found before and the 3 by 3 fact to n by n dimensions. If A is an n by n matrix, then the absolute value of the determinant is the volume of the n box in Rn, determined by those vectors. So in R3, the volume of the parallelepiped in R3 is the determinant of the square matrix with those as column vectors. But what I always found more interesting is like finding the area of a 2 box in R4. Like A is a non-square matrix. It's a rectangular matrix. And you can find A transpose times A is then a square matrix, right? Because for any matrix A that's an n by m, then A transpose is an m by n. So then A transpose is going to be an... I think of it this way. N by m times an m by n, and then these two terms cancel out in a sense, and you get n by n matrix. This is just kind of like shorthand to be able to remember whether it's n by n or m by m. The common, adjacent sizes cancel. So A transpose is then a square matrix, even for any rectangular matrix A. And then we can do some of this stuff with linear transformations. And we can transform a cube to an image box. That's kind of freaking cool. And then this is where it's super, super important and freaking used in higher math, in analysis. This theorem is super important because it becomes an application to calculus, for multidimensional calculus. Under a change of variables, we find differential forms, and we do some cool stuff about differential forms. We need to get some hand-wavy idea of sufficiently nice regions in Rn. If T is a transformation, the image of G under T has a volume of that. Yeah, and we get these types of diagrams. Region G in the domain of T, the image of G under T. And then we get this volume change factor theorem. G is a region in Rn of volume V, and we have a linear transformation with a matrix representation. Then the volume of the image of G under T is determinant of A times V, the volume in the domain. Super cool. I mean, I feel like this section was like really nice to read recently. So where is it in this book? Somewhere here, application to calculus, it says like getting into the analysis of this is outside of the scope of this book. But, I think this is what I'm thinking of. Having conveyed a rough idea of this topic and its importance, we leave its further development to an upper level course in analysis. Like, I do remember in an upper division course getting to seeing some of this like volume change applications in like multi-dimensional analysis. Yeah. The Jacobian is that linear transformation as a matrix. Yes, like we connect this to something called the Jacobian, and it's been way too long for me. I don't remember any multi-dimensional calculus. Cool, dude. So I can work a problem just for funsies, but this next exercise is it's actually just exactly like the first section where I think that the first section shows that the determinant of this parallelogram is, or the determinant of the matrix with those two vectors as column vectors is the area of that parallelogram. We already did number 5 last time, so for number 6, we write these vectors as column vectors, -5, 3, 1, 7. You could write them either way, but we want to consistently think of the span being column vectors in a matrix. -35 minus 3 is -38. So we're done with that one. And we could do a 3x3 determinant. We could do another 3x3. We could do a 4x4. But, you know, we already did a bunch of determinants today, and I'm ready to wrap this up. We're already 2 hours into the stream. Thank you, everybody. I had a blast studying math with you all today. As always, dude. I had fun. What's up, El Kooky? What's up, El Kooky? I hope you're doing well, dude. Thank you. This book is actually falling apart right now, so we need to get the Addison Wesley Publishing House to reprint this book so I can get a new one, because this one is getting really beat up, dude. Yeah, this book is about to fall apart. Yeah, I haven't properly learned multivariable calculus very well. Someday I look forward to like actually relearning that stuff, because it's so useful in like physics and electrodynamics and stuff like that. Yeah, we'll get there. We'll get there someday. I had fun. I mean, it might not be doing linear algebra right, but I still think determinants are just kind of fun little Sudokus to me. Thanks everyone for watching. If you enjoyed this, yeah, just consider that this stream is offered on a gratitude basis. Like, I'm offering the stream to you all free of charge, completely with no expectations. It makes me happy to be able to share my practice sessions, and it's very motivating to me, you know, to practice and to have an audience to practice with. But if you want to extend gratitude back, there's a few ways, a few options. I mean, literally the best way would be to share this stream with somebody. Like, if you know anybody who likes math, like, it's really fun to get friends in the chat. You could also leave a permanent comment in the comment section. Just say thanks. And then that way people who click on the VOD on the replay will see like that some people enjoyed this, you know, during while it was live. What else? I mean, this is, I don't know if it's gratitude, but it's also just an offer that I do have a Discord. If y'all want to join and help participate and help us build up a really cool little community. I think that there's potential here in trying to collect, you know, a bunch of math enthusiasts, like math nerds, dude. I really like some of the recent discussion that's happening in the math chat there. I have another channel that you could check out, which is called just at jcpractices or jcpractices guitar. And I am practicing classical guitar over there. Yeah, really would appreciate anybody who wants to check that out. And then yeah, monetary stuff. I'm not monetized yet on this channel, but I do have a Buy Me a Coffee. I don't have a Patreon. I think that they're a little too corporate. I like Buy Me a Coffee the best. But as I said, like, no expectation at all. Like, it just makes me happy to freaking make this stuff for you all. Thank you. Thank you for watching. Here are some options to help me build up, something cool that I have in mind. There's that, and I also am available as a one-on-one tutor, private tutor. You can email me, jcpractices@gmail.com. First lesson is free. I think I could help anybody. And yeah, like it's just nice to have a coach, I think, for somebody who's learning. And I feel like in theory, somebody who's even better than me at math, like I could be your student or something. I don't know. Or like we could work together and be like, study buddies in some sense. Thanks for watching. I gotta go. Bye. Appreciate you all. Bye.